Today, I want to start with a very simple question. Why are we still not traveling to other stars? I do not mean Mars or Jupiter or even Pluto. I mean other star systems. Places like Proxima b, Alpha Centauri, and those distant worlds that movies make feel like the next obvious step. In films, it all looks easy. A ship enters hyperspace in one place and appears in another part of the galaxy a minute later. Or it passes through a wormhole, like in Interstellar, and distance seems to stop mattering at all. Real space does not work like that. And to understand why, we do not need to start with Proxima. We can begin with something simpler. How long movement already takes even inside our own solar system. For this comparison, I want to use a very rough but useful baseline. Voyager 1 travels at about 17 kilometers per second. That is one of the best known and fastest interplanetary speeds in the history of spaceflight. From there, I will simplify the problem. I will estimate travel from Earth's orbit to the average orbit of each planet, as if you could travel almost in a straight line during a perfect launch window. These are not real mission trajectories. They are only a way to feel the scale. Real missions often take longer because of orbital mechanics, braking, gravity assists, and the fact that entering orbit is very different from simply flying past a target. If you use that rough method, Venus comes out to about 28 days. Mercury is about 62 days. Mars is around 53 days during a very favorable alignment. Jupiter is already about 1.2 years away. Saturn is roughly 2.4 years. Uranus is close to 5 years. Neptune is around 8 years. Pluto is a little over 10 years. And again, this is an extremely optimistic scale, not a real mission schedule with braking and arrival. It simply shows that even inside our own system, what feels far quickly turns into years. This is the point where people usually develop the wrong intuition. They think that if Pluto is about 10 years away, then the nearest star must be maybe 100 years, or 200, or 1,000. No. This is where the scale completely breaks. The nearest star to us is Proxima Centauri, about 4.25 light-years from Earth. The planet Proxima Centauri b orbits that star and is effectively at the same distance on human scales. It is the nearest known potentially rocky exoplanet, but it is still tied to a star that is several light-years away. Now add Voyager back into the picture. Voyager 1 is moving at about 17 kilometers per second. At that speed, if it were actually traveling toward Proxima Centauri, it would take more than 73,000 years to get there. That is the number people often round to 75,000 years. And that is not some dramatic exaggeration. It is just the result of very boring math. A light year is an unbelievably large distance. There is also an important detail that makes this even more interesting. Voyager 1 is not actually heading toward Proxima. Based on current calculations, in about 40,000 years it will pass within roughly 1.6 light-years of the star Gliese 445. In other words, the most famous interstellar probe humanity has ever launched is not really going to the next star. It is simply moving slowly through interstellar space along its own trajectory. That alone tells you how enormous real interstellar distances are. And this is where the main idea of this video begins. The problem with interstellar travel is not that we do not have a beautiful enough idea. The problem is that even our best real speeds are tiny compared with the distances between stars. The solar system tricks us. It is big, but still finite and familiar. Mars feels far away. Saturn feels very far away. Pluto feels like an extreme case, but all of that is still a world measured in astronomical units. The nearest star is not tens of astronomical units away. It is hundreds of thousands of astronomical units away. That is the gap between interplanetary travel and interstellar travel. So the next logical question is obvious. Why not just go much faster? Why not accelerate the way ships do in movies? This is where we run straight into basic physics. According to modern physics, and specifically special relativity, an object with mass cannot simply be accelerated to the speed of light. As speed increases, the energetic cost of pushing that object faster keeps rising, and as you approach light speed, the required energy becomes effectively impossible. So light is not just very fast, it is a hard boundary for ordinary acceleration. That does not mean very high speeds are impossible. It means the gap between very fast and like in the movies is enormous. Even if we learned how to travel not at 17 kilometers per second, but hundreds or thousands of times faster, that would still require gigantic energy systems, new forms of shielding, new engine designs, new spacecraft architecture, and a completely different mission economy. NASA studies on advanced propulsion and interstellar probe concepts do look at faster ideas, but even there, the conversation is not about jumping somewhere instantly. It is still about decades, centuries, or, in the most ambitious cases, extremely tiny probes. One well-known example is Breakthrough Starshot, which imagines gram-scale spacecraft pushed by lasers to about 20% of the speed of light, reaching the Proxima system in about 20 years. But that is a microprobe, not a human ship. And this is the second major break in human intuition. People usually ask, why can't we just build a faster ship? The better question is this: what kind of ship, with what mass, what shielding, what energy supply, and what crew lifespan could realistically be accelerated to those speeds at all? Because interstellar flight is not just about speed. It is also about energy, mass, radiation, protection from dust and gas at extreme velocity, system reliability over decades or centuries, human biology, and the total cost of the mission. This is where we get back to the movies. Why does everything look so easy on screen? Because cinema usually skips over the hardest layer of the problem. In Guardians of the Galaxy, there are hyperspace jumps and cosmic jump points. In Star Wars, there is hyperspace. In Star Trek, there is warp drive. In Interstellar, there is a wormhole. All of these ideas do the same thing in one form or another. They do not move an ordinary ship through ordinary space using ordinary propulsion and fuel. Instead, they either bypass distance, compress space, or use the geometry of space-time to make the trip shorter. That is exactly why they are so appealing. The real problem with interstellar travel is not courage. The real problem is distance. And most movie solutions are really just ways of cheating distance. The most famous real scientific analog to that idea is the wormhole. In general relativity, a wormhole is not a magical invention from fiction. It is a mathematical possibility, a particular type of space-time geometry. But there are two very important things to keep clear. First, faster-than-light travel is still not allowed within the best-tested theories we currently use to describe the universe. Second, a wormhole is not the same as moving faster than light. It is more like a shortcut between two distant regions of space, and that distinction matters. A wormhole in physics is an interesting theoretical possibility. A wormhole in cinema is a stable transportation tunnel that a ship can safely enter and cross. Those are not the same thing at all. Right now, we have no observed, confirmed wormhole. We have no technology to create one, no technology to stabilize one, and no demonstrated way to send a human spacecraft through one. So today, wormholes are not an engineering solution. They are a physical idea that has not yet reached the level of testable transportation. The same is true of warp drive. Yes, there are scientific papers that explore space-time metrics resembling what popular culture calls warp. NASA has also published conceptual work on warp field mechanics and advanced propulsion. But even those papers are not saying, we found a real engine that can take a crew to Proxima. What they are really saying is something much more cautious. If space-time geometry could ever be engineered in a usable way, it might radically change interstellar travel, but that is still not technology. Now, a good question follows from that. Does this mean travel to other stars is impossible forever? No. That would not be an honest thing to say. A better way to say it is this. With today's physics and today's technology, a full human mission to the nearest star remains effectively impossible. But that does not mean all interstellar efforts are forever impossible. Faster robotic probes may still happen. Laser sails may still happen. Extremely long-duration robotic missions may still happen. New forms of propulsion may still emerge from concepts that today are only theoretical. And this is where tone matters. There are two bad extremes in this conversation. One says, we will never do it. The other says, just wait a little longer, and we will be traveling like in the movies. Both of those positions are wrong. The honest middle ground looks like this. We already know how to send probes to the edge of the solar system. We already know how to detect nearby exoplanets. We are already developing serious concepts for interstellar probes. But the leap from a robotic concept to a human journey to Proxima b is not one more ordinary technological step. It may be one of the largest leaps in the history of civilization. And in a strange way, that makes the subject even more interesting. Because when you look at Proxima b, the question is no longer just whether we can imagine a distant world. The real question becomes, what level of energy, physics, engineering, and civilizational maturity would be required to make a 4-light-year journey stop being absurdly long? That is why I would frame the final conclusion like this. Inside the solar system, we still live in a world of difficult, expensive, but understandable distances. Mars is measured in months, Jupiter is measured in years, Pluto, in a very rough and optimistic sense, is measured in about a decade. But the nearest star destroys that intuition completely. At a speed of 17 kilometers per second, Voyager 1 turns the nearest star system from a distant mission into a project lasting tens of thousands of years. And that may be the clearest possible argument against easy fantasies about the next step beyond the solar system. So the problem is not that Proxima b is too beautiful or too far away. The problem is that between we can dream about it and we can go there stands one of the hardest physical barriers humanity has ever faced. And still, I do not think that is bad news. Because even if interstellar travel for humans is almost impossible today, the attempt to think about it is already changing us. It forces us to think about new engines, new energy sources, long-term autonomy, the real meaning of speed limits, and what it would mean to become a civilization that plans not only for decades, but for centuries and even longer. So maybe the deepest value of interstellar travel today is not that we will fly to Proxima tomorrow. Maybe it is that trying to answer this question makes us more serious as a species. Proxima b is not going anywhere. The question is not whether a road exists in principle. The question is whether we will ever become the kind of civilization for which a journey of 4 light years no longer feels impossible.